Hello everyone. Hello everyone. In this video, we will learn about inverse Laplace transforms. And let us see the definition of the inverse Laplace transform and also the various properties in the inverse Laplace transforms. Okay. So let me start with the definition of Laplace transform. So the definition of Laplace transform is The definition of Laplace transform is L of f of t. So how we were writing L of f of t? So we are applying the Laplace transform of f of t to a function in t. We call this as f bar of s. And what is the definition of the Laplace transform? Integral 0 to infinity e power minus st f of t dt. This is the definition of Laplace transform. Now L is called the Laplace transform operator. So by taking the inverse Laplace transform both sides by taking that L to the right side. So this we call it as L inverse of f bar of s. That means to a function in s, we can apply the inverse Laplace transform. So what we get is f of t. So f of t is equal to L inverse of f bar of s is called the inverse Laplace transform of f bar of s. This is our definition. F of t is equal to L inverse of f bar of s. Now that all the elementary results that we read in the Laplace transforms, we can apply the inverse Laplace transform and we can rewrite all the definitions. For example, we have studied Laplace transform of 1 is equal to 1 by s. Now, whenever we have a function of s, we can apply the inverse Laplace transform and we can write L inverse of 1 by s. This is equal to 1. Okay, similarly, all the other definitions will follow. We have learned that Laplace transform of e power at is 1 by s minus a. Now we will apply the inverse Laplace transform both sides and we write L inverse of 1 by s minus a is equal to e power at. Okay, and like that all the other definitions will follow and we can easily remember all the standard results. Okay, for example, if you have L inverse of 1 by s to the power of n, so how we will write L inverse of 1 by s to the power of n? This is t power n minus 1 by n minus 1 factorial, where n is equal to 1, 2, 3 and so on. Okay, so because we know that the Laplace transform of t power n is n factorial by s to the power of n plus 1. So now we are applying the inverse Laplace transform for 1 by s to the power of n. And not only this, we can write the inverse we can find the inverse Laplace transform for 1 by s square plus a square. So what is the inverse Laplace transform for 1 by square, where we have seen this in sine at? So this is now 1 by a sine at. Okay, next L inverse of s by s square plus a square. So what is the inverse Laplace transform for s by s square plus a square? It is cos at. Okay, next not only this, this side I will write. Okay, not only this, we have L inverse of 1 by s square minus a square. So what is the inverse Laplace transform for this? This is 1 by a sine hat. Okay, L inverse of 1 by s by s square minus a square. What is the inverse Laplace transform for this? Cos hat. Okay, and not only this, we have the first shifting property of the Laplace transform, and also we have seen the Laplace transforms when the function is multiplied with e power at. Now the same things can be written using the inverse Laplace transform by applying the inverse Laplace transform. L inverse of 1 by s minus a whole power n. This is e power at t to the power of n minus 1 by n minus 1 factorial. So you can easily compare the definitions also here. Okay, next L inverse of s minus a by s minus a whole square plus b square. Here you can observe that wherever s is there, s is shifted to s minus a. So this is e power at and this gives L inverse of 1 by s square plus b square. So what is 1 by s square plus a square Laplace transform? 1 by a sine at. 1 by s square plus b square Laplace transform e power at 1 by b sine bt. Okay, I think it is clear, right? Next. Okay, similarly L inverse of 1 by s minus a whole square plus b square. So this can be written as what? Sorry, just a minute. It is e power at s by s square plus a square, which can be written as cos bt. It is cos bt. Now 1 by s minus a whole square plus b square. So what is the inverse Laplace transform here for this? So this is e power at L inverse of 1 by s square plus b square. So this is now e power at, and the inverse Laplace transform for 1 by s square plus b square is 1 by b sine bt. So I will rewrite this again by taking another color. Okay. So this is e power at L inverse of s by s square plus b square, which is e power at into cos bt. Okay. Now, so let us look at some of the problems, simple problems that we have in the inverse Laplace transforms. And one of the most powerful method to find the inverse Laplace transform of a function in S is the partial fractions. Let us look at this. So finding inverse Laplace transforms using partial fractions. Let us find the inverse Laplace transforms using partial fractions technique. Okay, now let us take this with a small example. Let us look at one example on this. Now we have to calculate L inverse of 2s square minus 6s plus 5 by s cube minus 6s square plus 11s minus 6. Okay, L inverse of 2s square minus 6s plus 5 by s cube minus 6s square plus 11s minus 6. For this, I want to calculate the inverse Laplace transform. So the same thing can also be written as, okay, L inverse of 2s square. So this is also written as 2s square minus 6s plus 5. Okay, now we can observe that the denominator can be splitted into factors s minus 1, s minus 2, s minus 3, s minus 1 into s minus 2 into s minus 3. Now we will consider this part and we will apply the partial fractions. So I am not explaining you in detail, okay, about the partial fractions, and I can write this as a by s minus 1. These things are all elementary things. You can work it out to find the ABC values, right? So this side we have this entire factor comes here, right? So this entire part comes over here. You can put over here, and RHS you can write this as a by s minus 1, b by s minus 2 plus c by s minus 3. Okay. Now this is also same as, so what are the ABC values after calculation? I got the A value as 1 by 2, I got the B value as minus 1, and C as 5 by 2. Okay, now I'll just bring all those things here into the picture. 1 by 2 into s minus 1. Okay, and C value is minus 1, so 1 by s minus 2, and B value is minus 1, C value is 5 by 2, so 5 by 2 into s minus 3. Okay, now by the applying the linearity property of the inverse Laplace transforms, this can be also written as 1 by 2 into L inverse of 1 by s minus 1, okay, minus L inverse of 1 by s minus 2, okay, plus 5 by 2 times L inverse of 1 by s minus 3. Okay, so based on the given function, check whether that can be splitted into partial fractions or not, and you can easily apply the elementary results to find out the partial fraction for the given function and the inverse Laplace transform. So 1 by 2 times L inverse of L inverse of 1 by s minus 1 is e power t, L inverse of 1 by s minus a is e power a t, minus L inverse of 1 by s minus 2 is e power 2t. Okay, and for the last term this is 5 by 2 into e power 3t. Okay, so this is our answer. So using the partial fractions technique, the inverse Laplace transform for the given function can be easily obtained. Okay, now the other things you can just practice yourself, some of the other examples. Now I'll just brief you the shifting theorem in the inverse Laplace transforms. Okay, first shifting theorem. First shifting theorem in the inverse Laplace transforms. Okay, so as we are talking about the same inverse Laplace transforms, first shifting theorem. Okay, now what is the first shifting theorem in the inverse Laplace transform? If L inverse of f bar of s equal to f of t, okay, then L inverse of f bar of s minus a, okay, this is equal to e power at into f of t. This is the first shifting theorem in the inverse Laplace transform. If you replace a with minus a, so this can be also written as L inverse of f bar of s plus a is e power minus at f of t. L inverse of f bar of s plus a, this is equal to e power minus at into f of t. Okay. Now let us take one simple example and how this inverse Laplace transform is applied to a problem. Right now, L inverse of s plus 2 by s square minus 4s plus 13. So this is our given problem, and we observe that for this particular example, so the denominator cannot be split into factors. Okay, so it is difficult to apply the Laplace inverse, I mean partial fractions. Now for that, what I will do is I'll try to add and subtract 2 in the numerator. So this can be written as s minus 2 plus 4 in the numerator, and in the denominator, as I observe s square minus 4s, so I can write this as in the form of a minus b whole square. So this will be s minus 2 whole square. Okay, and s minus 2 whole square gives s square minus 4s plus 4, and I need 13, so I'll add some 9. Okay, which is sufficient for the denominator. Now if you observe the entire function, here in the numerator we have s minus 2, denominator also we have s minus 2. That means wherever s is present, it is written in the form of s minus 2. So we'll apply the first shifting theorem. This is something like L inverse of f bar of s minus a, that you can see the property just now. So this is e power 2t. L inverse of, okay, s minus 2 is replaced with s only now. Okay, s plus 4 by, this is s square plus 9. Okay, so s minus 2 is always replaced with s plus 9. So what we did actually here, L inverse of f bar of s minus a is e power at into f of t. What is f of t? L inverse of f bar of s. So s minus a should be replaced with s only. So this gives what for us? E power 2t. Okay, now I'll separate this into two terms. L inverse of s by s square plus 9, okay, plus L inverse of 4 by s square plus 9. Okay, so for both the terms e power 2t is present. Right, now we will apply the inverse Laplace transform, all those standard results to get the answer. So what is this now? It is equal to e power 2t. L inverse of s by s square plus 9. 9 is 3 square. L inverse of s by s square plus 3 square is cos 3t. Okay, plus 4 is a constant, and we can multiply and divide this with 3, so that it will be 3 by s square plus 3 square, which is sine 3t. Okay, so this is our final answer. Okay, in that way the inverse Laplace transform can be applied using the first shifting theorem. Okay.